It's finally time to code up the transformer class. So this is actually the last class and maybe the most important class that we're going to write in defining the GPT model. So the next problem is actually going to be writing the GPT class, and we're going to use this transformer block class. And this transformer block class that we're about to write is going to make use of the multi-headed attention class that you've previously written. So the transformer block is actually this gray rectangular block that is repeated nx times in this diagram. And this itself is a giant neural network layer that we're going to use in the GPT class. And there is also like a really in-depth explanation on the transformer block over here that explains like layer by layer, breaking down and explaining what every piece of this block is doing. I recommend checking that out. But in this video, we're also going to go over how the transformer block works at a general level, and we're going to code it up as well. And the forward method for this class. So this is transformer block class is going to subclass nn.module, and it's going to have a forward method because we're going to pass some sort of input in to the transformer block and get some sort of output. And it needs to actually return a tensor that is b by t. T is our context length by model dim. Let's just call that capital D. And one thing I want to clarify is that in the previous problems, when we were introducing attention, I kind of made a distinction between embedding dim and attention dim, but they're actually the same thing. There's just one giant parameter called model dim, and they're the same number. And then model dim, mod num heads is 0, and then the head size for multi-headed attention is model dim divided by num heads. So let's make some sense of this example. We don't really need to worry about the numbers, we just need to understand the shapes. So the input, we call that embedded, since it's actually the output from the embedding layers of this neural network right before the transformer block starts in the diagram that we just showed. So the input is b by t by d, where d is the model dimensionality, and the output is also b by t by d, the model dimensionality. And we're told that the model dimensionality is 4, as we can tell over here, that we have these 4 columns over here in the input and the output. And then we can actually infer from this that t equals 2, the context length is 2, and we can also infer that the batch size, the outermost dimension, is 2. So now let's jump into how the transformer block works. So one small change from this diagram is that this middle multi-headed attention part, which is actually factoring information from the left part of the transformer diagram, we're not going to incorporate that at all. Transformers like ChatGPT only use this right part of the transformer, which is actually called a decoder, although that term is not super important for now. They only use the decoder and they don't actually include the left part of the transformer at all, so we're just going to completely ignore that. The next thing that we need to actually explain is in the original transformer diagram, they went ahead and described this as add and norm over here, and the same thing over here. But it would actually be more accurate to say norm and add. Researchers have found that norming first and then doing our skip connection or add, and we'll definitely explain what these actually mean in a sec, but norm and add is actually what's done. So let's explain the norm layer. This refers to something called layer norm, which you can actually use as a layer, make an instance variable inside the constructor for the transformer block class, and that's going to be nn.layerNorm, and you simply pass in model dimension. And this is going to tell this layer that whatever tensor is passed in, it's b by t by d, go ahead and do the normalization along this dimension. And what we mean by normalize is when you have some sort of data, to normalize it just means to really center it around some sort of fixed mean and standard deviation. So this is kind of an example of normalizing data. We can see that the data is kind of all revolved around or centered around the mean, the symbol mu. The mean is the most common data point, and the standard deviation just kind of reflects the width and how the data is stretched out from left to right. And researchers have found that this really does boost the performance of transformers. And researchers are actually not entirely sure why layer normalization seems to improve the training of neural networks, but it seems to be something along the fact that we start off with some random distribution of the weights in the neural network, and we don't want them to change too drastically. That actually makes our training process really unstable. So next, let's explain the add, also known as skip connections. So, and then one additional weird thing that is mentioned in the problem is that the norm is actually going to come before the attention instead of attention before the norm. So now we can actually explain this add in add and norm, also known as skip connections. We have our input to the transformer block X, which is actually going to pass through layer norm, and then the output of layer norm goes into multi-headed self attention, but then we can actually add the unchanged X all the way back to the output of multi-headed self attention, and then this is the output. This is the output of at least the first part of the transformer block over here. This is the first part of the transformer block, and how we would actually do this in the forward method is we would actually just say something like X plus multi-headed self-attention of the norm. Remember, we're going to norm first and pass in X into the norm. And again, this is kind of covered in more detail in the transformer block background video, but the short explanation for why this skip connection over here, actually letting some portion of the input bypass these layers entirely and actually adding X to the output over here, is that having some sort of additive term instead of having only multiplication in this neural network. Having some sort of additive term seems to actually smooth out our gradients and actually slightly mitigate the exploding and vanishing gradient problem during training. So then the output of this first part of the transformer block over here is then passed into the second part of the transformer block over here. And again, we're actually going to apply the norm before the feed forward, even though in the original diagram, it actually says feed forward and then norm. So we're going to do norm and then feed forward and then add this component, which came out of the first part of the transformer block. We're going to add this component back in over here, and that's our second skip connection. So what's the whole point of this feed forward component of the neural network? Well, this is also called a multi-layer perceptron. Multi-layer because we're going to have multiple linear layers and then non-linearities. That's kind of maybe the perceptron part of this term, if you want to think of it that way. It's also called a vanilla or just a standard neural network. Well, if the attention component of the neural network over here is actually our communication mechanism, this is where we let the tokens talk to each other. Again, I highly recommend understanding multi-headed attention through those coding problems before we move into kind of this transformer block problem. But if attention is our communication mechanism, then the feed forward part of the neural network, this is actually our computation mechanism. This is where we have a bunch of neurons in each linear layer of this feed-forward neural network that are learning a bunch of weights, biases, W1 times X1 plus W2 times X2, doing a ton of linear regression. So after we've let the tokens talk to each other, after we've let the tokens do their communication, we want to let the tokens have some time as they pass through these linear layers, and of course non-linearities like ReLU as well. We want to let the tokens actually do computation, and this is all going to factor in to the model's prediction in the final layer or two where the model predicts the next token. And just looking ahead a bit, this is not going to be part of the code for this problem. It's going to be part of the next problem where we actually code the full GPT class. But just looking ahead a little bit, after the model has done all this communication, all this computation in this transformer block, and then in the GPT class, by the way, the transformer block is going to be repeated some number of times. So we would take the output of the transformer block, pass it back in, and do this some number of times, maybe like 6 times, maybe 12 times. But the point is, after the model has done all this learning within the transformer block, let's actually take a look at what's to come ahead. There's going to be a linear layer where in features is model dim. This should make sense given the dimensions used in the transformer block. And then we're actually going to project to a dimension of vocab size. So this linear layer has vocab size different neurons. We're going to have essentially vocab size different numbers for every single token at every single time step. And the reason we have that many different numbers being predicted is because each number is going to correspond to a probability or the chance that that corresponding token comes next. And we know we have exactly this many different tokens in our vocabulary. So we're going to have the possibility that any one of them could come next in the sequence, as this model is learning to predict the next token. So we're actually going to need to have that many different numbers to get the full prediction. So then just to clarify, just looking ahead a little bit as to how this model is going to be trained once we've fully written the GPT class, is we know we had a B by T input, a batch of sequences, each of length capital T. And then, the model, if you've solved the GPT dataset problem, I highly recommend solving that problem before doing any of these transformer problems. Well, we know that we have B by T labels because we know that for every context or all the sequences of tokens, the model is trying to predict the next token. So the correct answer or the labels is just actually the tokens kind of offset by 1. And that is kind of become clear in the GPT dataset problem. And then our output is B by T by V for every single batch. And then for every single token, every single time step in this sequence, then we have a vector of size V, the vocabulary size, which we're thinking of as a list of probabilities. The softmax layer over here is going to make all the numbers between 0 and 1, so they actually can be interpreted as probabilities. We have a bunch of probabilities for which token is going to come next in the sequence. That's the model's prediction. And then the loss or error is going to be calculated using two things: the model's prediction of the probability for what token came next. Again, that is in this vector of size V. And then we actually know what token comes next. That's in our labels. The labels were extracted from the raw data set, and then that is used to calculate the loss. We drive the loss down during training using an optimizer and following the gradient descent algorithm. And in the end, we actually have a model that can predict the next token really well. Before we jump into the code, I just wanted to clarify one thing. In the constructor for the transformer block class, you will definitely need to make two different instances of nn.layerNorm, one for this layer norm and one for this layer norm, so that we can learn different parameters across training. So now let's code this up. We know the first thing we need is our instance of multi-headed self-attention. So we can say self.multi-headed self-attention, and we can use the inner class below. So self.multi-headed self-attention, and the only things that we really need to pass in there to this constructor, well, why don't we check the constructor? For the constructor for multi-headed self-attention, we just need to pass in model dim and num heads as that is visible over here. So scrolling up, we can actually then take a look at that, and we can pass in model dim and num heads. So model dim and num heads. The next thing we're going to want to do is make our first layer norm. So self.first layer norm is nn.layerNorm, and this takes in model dim, the channel or dimension along which to normalize. Then we need our second layer norm, so second layer norm, and that's nn.layerNorm, and again, we want to pass in model dim. And we're also going to need a feed forward layer, right? The vanilla neural network. So we can say self.feedForward equals self.vanilla neural network. This is actually given below if you want to check it out. It's just a couple linear layers with a ReLU function thrown in between, and then we're going to go ahead and again pass in model dim. And that's it for the constructor. Now we can go ahead and write the forward method. So to know that for the first skip connection, or the first part of the transformer block, we just want to take embedded, which is like X that we talked about earlier, and then we're going to do self.attention or self.multi-headed self-attention, and then we're actually going to invoke our first layer norm here. So self.first layer norm, and then to there we are actually passing in embedded. So this does reflect the diagram that we talked about earlier. And then we can save this in a variable called like first part. This is the first part of the transformer block, the part that doesn't have the feed forward layer. And then what we're going to want to head and do is actually take first part and then go ahead and add the result of the second part. So then we can go ahead and say self.feedForward, and here's where we'll invoke our second layer norm. So you can say self.second layer norm, and we're going to go ahead and pass in the first part. So this also does reflect the diagram that we talked about earlier. And this is actually exactly what we want to return. We just need to round it. So we can say that this is our result, like res, and then we just round it. So we can return torch.round of res. and say decimals equals 4, and we're done. And we can see that the code works. We've finally written the transformer block, and in the next problem, we're going to code up the GPT class. So that's definitely going to be an interesting problem. So definitely check that one out next.